Hey everybody, hello and welcome to the Tech Report podcast. We are here with special guest David Kanter of Real World Technologies and the Microprocessor Report. And we have the chance this evening to talk about Intel Skylake processors, especially the architecture. They've done a big reveal in the wake of the Intel Developer Forum. We were both at the Developer Forum, attending the sessions and talking to the architects. We now have a lot of stuff in our noggins we know about this new CPU architecture and about these chips. And we have a ton of questions already queued up from you guys, and we are going to talk about them. If you are joining us in the live stream on Twitch, then feel free to go ahead and put additional questions into the chat. We'll try to collect those as we go and answer as many as we can as we go. David, are you ready to do this?
Yep, let's go.
All right. So we have, David, we have an article that I have written about this that is not completed.
Yeah.
So I will bring this up for you guys so you can see. There are words, and there are like little diagrams and
I can't
subheads.
see this now.
You can't. Oh, I'm sorry. Well, you can watch this later, but I'll give you a link if you want it. Actually, the link is in the document I shared with you.
Oh, okay. I see.
And it's not done. It's not even necessarily correct yet, so don't tech edit my stuff yet. But I have attempted to start on covering Skylake, but I've just been, after IDF, it was an intense week, and I got back home, and it's just allergy season in Missouri, and just knocked me on my butt. And so I have not been able to complete this, but I'm trying to work my way through. I have like a 1,300 word outline, and
it's a hell of an outline.
Yeah, I'm not smart enough to write just without an outline, so I have to outline everything first. So I know exactly what I want to say, but I haven't said it. It's kind of anyway. But there's a lot to Skylake. David, what the article kind of opens up by saying is that these are SoCs now, not just CPUs. They're systems on a chip.
Yeah.
And they have so many pieces, right? It's the CPU, graphics, memory controller, ring interconnect, power management, which is a whole chip thing, lots of I/O, and they keep bringing more functions into the CPU over time.
Oh yeah,
dude, my mic just took off on me. Sorry about that. Anyway, I said they just keep bringing more functions into the CPU over time. And so what happens when you get a refresh like this, which is a new architecture, it's a talk in Intel's Tick-Tock development setup, is almost everything changes, right? And so it's not just new CPU microarchitecture, it's new SoC architecture almost across the board. Like they built on what they had before, but the modifications are everywhere. And so it's a ton to cover. And so that kind of is the context for this.
I think they kept the PCI Express 16 unchanged. Yeah,
except that on the chipset level they changed it, and they added more for the link to the chipset in the bigger versions of it. Yeah, it's
DMI3. That's right.
And so there's some of that, and then like the rest of the I/O block, especially on the mobile version, has like
totally different.
Has tablet I/Os. It has an integrated ISP so that it does camera stuff right there on the chip, right? Image signal processor, and all that is like new and different, and actually it's a reasonably capable ISP. It's like 4 cameras, 2 concurrent, 13 megapixels, plus 1080p multi-stream video. I don't think it does 4K yet, but the media block decodes and encodes 4K. It's just the ISP that I'm talking about, but it's a ton of stuff. So there's more to cover than we could probably manage to cover. I think that probably one of the most interesting things to talk about with you is the CPU architecture and microarchitecture.
Yeah.
So we speculated about this when we had our last live stream about Skylake, David.
Yep.
And I think that most of the things that we thought were true.
Yep.
And then maybe a few surprises about how extensive some of the changes were that didn't show up when you tested the desktop parts because they're built for low power. Like the benefits are going to be in low power devices.
Yeah, that's definitely true, especially for the power management. I mean, I think that was just not super helpful for workloads that peg it at 100%.
Well, not only that, but when we tested with Windows 10, although Speed Shift Power Management requires Windows 10, Windows 10 was not yet patched for it. I think it is now. I think like if you have the latest updates, they just came out with one that enables.
Oh, really?
It. Yeah, but it hadn't yet been. And it's possible that there's a little more goodness out of Skylake now than when we initially tested it. Although, like you said, probably not as much in those higher power envelopes as you would have in a mobile device. So, where to start is a tough question, but let's go with my favorite slide that they presented, David, which is the size of the out of order machine. And basically showing us, what the window looks like, how much stuff they can have in flight, how many entries they have in the different structures, and how that has grown from Sandy Bridge to Haswell to Skylake. So, take us through this. What does this look like to you?
I mean, so broad picture, it's an evolution. Everything is incrementally wider. The out of order window or the reorder buffer is, it's 10, 20%, about 10% wider. And the interesting thing is the number of loads in flight didn't change, but the number of stores did go up considerably. And I think part of that is maybe motivated for adding in the scatter. So for those that don't know, when you have wide vectors, one of the things that's highly advantageous is to do a strided load, which is called a gather, or a strided store. So rather than getting everything from a cache line, you might say, well, I want to store back 16 different data items, and then they're all offset by a variable amount. And you could get really lucky, and they're all offset by the element size, and then it is one cache line. But a lot of times, you might be writing back to a different type of data structure, and so they might be separated by 4K. Who knows?
Yeah,
and so the way that's handled in Skylake most likely is that they're going to crack it into multiple UOPs, and so they may want to have the ability to have more stores in flight. Then, the other thing, and I'm trying to remember, so Scott, were you in the second Skylake microarchitecture session?
I went to the power one.
Okay.
Is that the second? That's the second one. Because I missed the graphics one to go to the second.
They did a replay with.
I didn't go to the replay.
Yeah, so there, I actually asked them, seriously, 97 entry scheduler? What the hell?
Yeah, that's a weird number, right? 97. It's odd. It doesn't fit computer stuff.
Yeah. Yeah, exactly. I think my question to him was like, that's not a power of 2. Fine. It's not even a multiple of 2, right? Like, how do you get something like that? And so there's a guy there who was the core microarchitect who was not giving the presentation, but he was in the audience, and I went up and talked to him afterwards. And I didn't get a complete explanation, at least to my satisfaction, in terms of understanding how things work. But what he said is, the scheduler is not really as simple as I've portrayed it in my articles, and that doesn't surprise me, right? One of the big challenges is that when someone asks, well, how big is the reorder buffer, or how many loads can you have in flight, you'd like to give a concrete answer. But invariably, any simple number will be false, right?
Right.
Just as a simple example, right, with 16 loads possibly per gather, right, we've only got 72 entries in the load buffer. It's quite possible that the gather, might take up 16 of those at once. I actually don't know, but you could see the situation where you end up where you're like, yeah, sorry, you only get like 8 loads because they're all gathers. So I think what's going on is that there may be a separate scheduler or separate queue or some sort of structure that differentiates between memory UOPs and execution UOPs that just write to registers. And it's also possible that they could be doing some sort of internal bundling where, for example, a bunch of things that are part of one instruction but multiple UOPs end up sitting as one scheduler entry.
Right. And because we've seen that type of packing that they've done, with related instructions.
Yeah, I mean, so they do that in other parts of the pipe, and certainly if you look at IBM's high-end power processors, they end up issuing these sort of complex bundles that have very specific rules in the out-of-order window in order to keep the structure smaller. And so, I think in the Power 4, you could have like 4 or 5 instruction bundles, and if there was a branch, that had to be the last one. And so it got into these really complex rules. Now, I don't think Intel's doing that, but there's a lot of different creative ways to design a scheduler. And the key here is, this is a structure that we have to search for 8 things to issue every cycle. That's pretty power hungry. And so you don't want to light up the whole thing all at once. And so I could see that they might have said, okay, well, let's have something that is mostly unified, but a step in the direction of a truly distributed reservation station-based system like the Knights Landing Corps or Silvermont or other microarchitectures in the past.
Right. And so that number being weird is a clue to the structure not being as simple as we thought. And
exactly.
Yeah. So let's I'm going to step back real quick because I want to kind of set some context for this for those who aren't completely familiar with this. Modern CPU does a lot of, I called it dark voodoo magic in my write-up. In order to take a serial stream of instructions, some of which, the inputs are dependent on outcomes, from earlier in that stream, and try to basically break that stream up and execute chunks of it in parallel as much as possible. And then magically, deal with all the dependencies and the weirds like if this, then that's. And at the end of the thing, reassemble everything and get the right answers out and have improved performance by doing so. And that's hard. And yet, Skylake is one of the, at least amongst consumer chips and things like that, one of the biggest examples of this kind of thing. And they've got a bigger out of order window now than Haswell substantially, and even more so over Sandy Bridge. They're just doing more of this dark voodoo magic in order to make things work. And yet, David, they seem to have improved power efficiency even as I measured it in terms of energy per task. Compared to prior microarchitectures. That seems hard. That seems...
It certainly is, but I think they've gotten a lot more clever about how they do things. So I know when I talked to one of their architects, he actually said that they can clock gate. So let's back up for a second and just do a super quick microarchitecture primer. So what happens is you fetch a bunch of instructions, you decode them, and then you slap them into the out-of-order window. And so that really governs how many UOPs can you have in flight at any given point in time. And there's additional restrictions, which is for ordering reasons, every load needs a load buffer entry, every store needs a store buffer entry, everything also needs to go into the scheduler, and then the oldest instructions from the scheduler are grabbed and then issued out to the execution units, right? And you also need an integer register file entry for the output of an integer instruction, or an AVX and floating point register for, the appropriate kind of instruction. And so you've got a lot of state that you're carrying around, and one of the limitations you're trying to work around is that we've only got 16 registers, 16 integer and 16 floating point. And so what we want to do is, in reality, we have 180 integer registers, but the compiler can only see 16. and ditto on the floating point side. So part of the renaming process is to say, oh, at time t, register RAX is actually register number 7, and then RCX is register number 8, but then RCX at time t plus 1, that's going to be register like 32 or something, right? And then that lets you get these instructions which might be referencing the same logical register to actually execute at the same time because you've given them different physical registers. And so, yeah, it does use up a lot of power. But one of the things that's interesting is they said, well, you know, now we've started to clock gate things when they're not necessarily in use. Like, for example, right, one of the biggest problems that anyone has to deal with is a load or a store. In particular, load misses are a pain in the butt. And it's, you know, 4 cycles if you hit in the L1 cache. It's about 10 or 12 if you hit in the L2. If you hit in the L3, maybe 20, 25, 30. It sort of depends. It's a little model specific. But if you miss in the L3 cache, you're hosed, right? It's going to be about 50 nanoseconds, which is, you know, depending on your processor speed, somewhere between 100 and maybe 300 cycles. And so, you know, one of the things that you could imagine doing is being like, well, okay, we now have a bunch of loads that we've missed on. This thread can't go any further, so we ought to clock gate it down because we're really waiting for these loads to come back and then we can progress. Mm-hmm. Right? And of course, you know, God help you if you happen to hit that load that misses in the memory and goes to disk through the virtual memory. It's going to take forever.
Right, yeah. I mean, you might as well just go home.
So,
right?
So when you say that they're clock gating, you're talking about clock gating registers?
So I didn't get into a detailed discussion, but it sounds like what happens is, you know, they can detect certain phases of execution when you're more memory bound. And then, yeah, you could imagine clock gating the scheduler. You could imagine clock gating parts of the integer register file, parts of the floating point register file. There's so many different ways to do this. Like, you know, you could say, oh, well, if we have 2 threads, well, one gets half of the scheduler and the other gets the other half. Well, what if one of those threads stalls? Then maybe we should clock gate off half the scheduler. Right. I mean, I don't know how they implement it, but there's a ton of tricks you could play like that.
Right, and obviously they're pulling out the tricks. This is a late-stage architecture that has a lot of complexity and yet manages to be more efficient than prior ones.
Yeah, exactly. And I think that's the bottom line, is that as these structures get bigger, they also have to get more efficient.
Yeah. And
right.
One of the big, well, let's talk about, there's so many things to talk about. Let's talk about one of the big things that has been expected for Skylake is, we already mentioned vectors, is AVX 512, right? And this is about sort of parallel math, doing especially like floating point usually, like crunching through lots of stuff at once. And the more that you can do in parallel, the higher your throughput, the better off you are in things that are high payoff, whether it's video encoding or other types of visual image processing or, you know, scientific computing. There are
so
tons
you've
of
actually
things.
missed one of the big ones, which is like not totally obvious, but actually memory allocation. So for anyone who uses Linux or is a programmer, right, one of the things you do all the time is call malloc, which basically says, all right, give me a chunk of memory that's yay big. And, you know, typically you're not going to ask for small amounts. And so the first thing you have to do is you have to go through and zero that all out. And so if you have the ability to do a 64-byte read and write, that's great because you can nuke the whole cache line all in one fell swoop.
Right. So that's a big thing for Skylake.
Yep.
And
except for the clients.
I say the versions of it that we now have, and we have a ton, right? We have a ton. We have Core M's, Core i5, Core i7, Core i3, all sorts of desktop and laptop and tablet
station,
right? And none of them have AVX 512.
and what Intel has kind of hinted at, we know this is happening. They just say, well, talk to us about AVX 512 when the Xeon comes out, like the server version. And so this is interesting because Intel has typically, in the sort of since like titanium was no longer the thing, kept the same basic core design across all of their stuff. And they're not changing entirely from that strategy, but they're in this way bifurcating their cores, right?
Yeah, I mean, so and let's be clear, like Intel has a long history of fusing things off in order to maximize the amount of money they get out of consumers, right? Basic marketing stuff.
Yeah, you don't get this feature unless you pay for the Core i7. Yeah,
right. And this is different. I mean, they're not fusing off anything. There is literally no AVX 512 in this chip. Mm-hmm. It's just straight up not there. And, part of that is it uses a lot of area, and they probably found that the performance gains weren't all that substantial. And so, if you look at this, I don't really know how much area it uses, but let's say it's a millimeter squared. I mean, times 4 cores, that's a lot of area. I mean, that's millions and millions of dollars to Intel's bottom line. And if consumers really aren't going to see a benefit from it, like, why stick it in and just, lower your prices instead? And so right. I think that's an element of it. The one thing I was really disappointed by is, I'm going to wag my finger at Ronak in case he's watching. I thought it would make sense to microcode the AVX 512 instructions.
So it's compatible on the client versions, even if it's not as fast. You could run that code on whatever.
Yeah, and so it's hard. I mean, it's not free, right? Microcode takes space, and you can introduce bugs, and there's certainly some complexity there. But one of the things is, like, when I look at Intel's instruction set architecture across chips right now, it's a mess.
And now we've got a bigger mess, kind of. I mean, we've got
Skylake client, Skylake server, Knight's Landing, which, oh, by the way, isn't totally 100% compatible with Skylake server, right? There's different AVX 512 extensions in each one. And then you've got the Atom line, which doesn't even have AVX at all. And, this is one of those things where, frankly, I like that Intel can extend their instruction set. I think that is an advantage over ARM because you can add in new and interesting things and, accelerate whatever you want. But there is something to be said for uniformity and just really having software that runs everywhere.
Yeah. Well, so 2 questions about wide vectors, though. I mean, first of all, they've already had some issues with like, they've got a separate clock for AVX 256 on the Xeons. Yep. It burns a lot of power to have a wide vector like that. Like, does it really make sense for a client version of the chip?
Well, I mean, look, so you could design it. So actually, let's take a step back. So one of the things that's new in Skylake is the AVX units are power gated.
Right.
So that's pretty cool. I mean, in theory, you could probably arrange your power gates so that you really don't pay a leakage power penalty, and certainly you're going to clock gate them anyway. So
right, but when they're active, they're going to
but
impact your power budget quite a bit.
Yeah, but again, it's always a net win.
Right. Okay. Except for that, it costs more to put that in silicon.
Right, and so that's the issue, is like someone took a look at it and probably said, well, it's not that helpful, just keep it out. So, there's a physically different layout. And what you alluded to earlier is that this is really the first time Intel's ever done that in x86 history.
Yeah.
And we also see that in Knight's Landing. And so you weren't at Hot Chips. But, I originally had some speculation about what Intel was going to do in Knight's Landing. And, I said, well, look, there's like 4 options. They could use the P55C core from Knight's Corner, but that thing sucks and they should not do that.
Yeah.
Right. You could use a big out-of-order core and like try to slim it down or something. or just eat the die area hit. You could use Silvermont, or you could do a custom core, right, and maybe start from one of those two. And so what they did is they actually started from Silvermont, and they have a totally different core in Knight's Landing. It's got like 2 load ports. They're each 512 bits wide. I mean, it's really different. Like the way the instruction cache works is different. And so that's cool. But the thing that is interesting is now we see these 2 examples of Intel taking basic microarchitectures and changing them for specific products and for specific markets. And I think in some ways that's kind of cool because now we have like more variety, more articles to write. Great. Yeah. And more creativity.
But it's hard to program.
Yeah, no, I mean, these are out-of-order cores.
I guess, okay. There are 4 specific things. But, I don't know. It does get weird, right?
Yeah, I mean, but it's a sign of the times, and I think it's an interesting insight into how things have changed at Intel.
Yeah.
Is that they really are not saying anymore, like, one size fits all. It's, okay, we're not going to customize a core for just anyone, but look, if it really makes sense, make it work.
Right. So here, another question about wide vectors. To what extent does it not make sense to do that on a chip that has an integrated GPU? I mean, at some point, you can do your floating point math over there, especially if it's something that is easily parallelizable, right?
Yeah, I mean, if they wrote it in OpenCL.
Right. Or if we had something, some other avenue into getting hold of that floating point power. But it's there, it's on the chip, it's parallel.
Yeah, I mean, certainly that's possible, but I mean, there's definitely a lot of limitations that go with that, right? I mean, I think the moving from x86 to OpenCL is non-trivial.
Right. Now go ahead if you want to elaborate. Nope. We had a good question that comes up in this context from Chuckula. I'm not going to read his question because it's long and whatever. And he says out of order execution with a OOOE, and that's enough. But here's the thing: we know that Skylake has a number of changes, right?
Yep.
L2 cache bandwidth is effectively up because it's smarter. Better logic, better miss logic, and some things like that. L3 cache bandwidth is a little bit up as well. The core's access to the cache is faster, which I think is the big win on the L3, they said.
Is it lower latency?
No, they were saying that maybe it was in the... my notes said L3,
so it's the fabric. I think they made some changes.
The fabric as well, right? So the ring fabric is the same width and speed, but the stations are faster. And they got, without really increasing power, effectively twice the bandwidth on the ring.
Yeah, that's one of those things where I really want to see the hot chips paper or talk to the architects to fully understand. Because there's obviously a lot of optimizations you can do, but...
So what they told me was that in prior generations, they couldn't necessarily access things every clock cycle at the stations. And they have a little more buffering, but they also have improved flow control and every cycle access in order to increase the bandwidth. So it's really the local station hardware that they had to improve to get the ring to be faster. But all these things are faster, right? The L2 cache, there's to some extent last level cache, the ring fabric, and going out to memory, they've got DDR4 now, so they have more bandwidth to memory. And then going back to the L2 caches, they made a change that's kind of interesting. They're now less associative. They're 4-way set associative for the L2s, and there's maybe some reasons behind that. But to what extent, Chuckula kind of wants to know, are these improvements, all this additional bandwidth, meant to support AVX512, even though that's not in the client version, right? I mean, you do all this to enable wider vectors to give you benefits, because otherwise you don't have the data path to make it work. To what extent is that why we're seeing all of this?
I mean, that's tricky. So, like, if I look at like a lot of the optimizations, I think a lot of the stuff in the cache hierarchy might still be useful, but certainly there were changes to the data cache that I think are uniquely for AVX 512.
The L2s?
L1. No,
L1, okay. L1D.
I mean, the L2, right, the L2 has never been able to, like, really max out bandwidth. And I think that was really the ratio of cache latency to number of L2 misses that could be in flight at any given point in time. And so now they did add a couple of fill buffers so you can have more L1 misses in flight. And maybe you can have more outstanding L2 misses as well, but that's probably all limited by the number of mishandling registers in the L1. But yeah, I think some of that may be a little bit related to AVX 512, but more misses, that's just going to allow you to, better bandwidth from the L2 allows you to swap in newer data to the L1. So,
yeah,
I mean, I think it's generally useful, but you're certainly going to see a lot more pressure with AVX 512.
Yeah, and these improvements don't just benefit AVX. We should say. I mean, we've measured performance benefits generally, and then sort of in non-AVX workloads that are targeted, you can still see, okay, the cache is faster. It benefits everything, not just wide vectors. But yeah, so the L2 cache is the four-way set associative thing. Why is that what they chose, and what does it mean for the Xeons maybe?
Right. So Intel's L2 cache, since they moved to a 3-level cache, has been 256K, 8-way associative. Mm-hmm. My theory is that for the server chips, they're going to go to 512K and 8-way associative. And so then they said, well, okay, that really helps on servers, not so great for clients. So let's just cut it in half. We'll make it 4-way set associative. And, that'll take a small performance hit, but it's probably not the end of the world.
Yeah, and they did other things to make up for that. The L2 performs better than the prior generations. So.
Yeah, exactly. I mean, so more associativity is not always better in the sense that if you have 8 ways in the cache where a piece of data can reside, you need to check all of them simultaneously or, pay a latency penalty to sort of check them sequentially or something like that in order to figure out if you have a cache hit. So, going from checking 8 things in parallel to 4, could buy you a little bit of power, could buy you a little lower latency. But, realistically, I mean, more associativity is generally better, and I really just think it's motivated by changes to the server processor.
Right.
And high-end desktop as well, right?
So, okay, so let's talk a little bit about the power-saving stuff in here, because I feel like we should cover that. We got a ton of questions, and I also want to get into some of this DirectX 12 graphics stuff that people are asking about if we have time. But so let's real quick. Fiverr is gone.
Yep.
So there's no fully integrated voltage regulator here.
Yep.
That means fewer voltage supply rails. And they basically straight up said the one VR couldn't be optimal from 4.5 watts to 91 watts, which is what the requirements were.
Yeah.
And also that the requirement...
Well, not just that. I mean, I think one of the other things is, if you remember, they really struggled with the thickness of the package inductors.
Yeah, the Z-height on Broadwell was a problem, right?
Yeah, and if we look at Skylake, the Z-height is even lower. So
thinner tablets and devices.
Yeah.
Yeah. They also said that basically they had defined the whole product. They had all of their S and U and all of the different 18 or 15 watt up to 91 watt stuff defined. And then the requirement came in for the Core M style 4.5 watt one. And they had to have a moment where they stopped and said, whoa, what do we do now? And I wouldn't be surprised if that was in the moment where they said, Fiverr's getting the boot. Because they did say they had to make changes, and they didn't say specifically what they were. It was Shlomi Weiss who said that, right?
Yeah. Yeah, I know. I mean, that seems pretty reasonable. I mean, I think the Fiverr was probably much better for higher power. I mean, it wouldn't surprise me to see it in the Skylake server.
Well, okay. We talked about this. You were talking about a different form of voltage regulation that linear VRs. You were wrong that it's in Skylake. But you read the paper. This is the interesting question. The paper that you read was about 14 nanometer implementation of this, right?
So it's in there.
It could be in the server one, or it could be...
No. The linear voltage regulator is in Skylake client.
Somewhere.
However, it was disabled for the cores. And what they said is, at the end of the day, with a core, it's either on or it's off. Right? That's the way it works, right? It's not like, you can adjust the voltage and you can adjust the frequency, but you don't need to change the voltage on a cycle-by-cycle basis, really, because, right, if you remember the speed step 2, and we're getting a little bit ahead of ourselves, but they adjust frequency and voltage every millisecond.
Right.
That is a long time. And so you can get a voltage regulator that can, run at 1 millisecond, no problem. So I think what they took so the linear voltage regulator is used in the uncore.
Okay.
Right,
so
because
it's there.
That's the kind of thing that you don't really shut off, but, do you really need to be running the thing at max clock, at max clock and max voltage if all you've got is, like, one core waking up to, like, drive Skype and beam, your ugly mug out to the world?
Right. That's interesting because they said that the ring was the same supply rail as the cores, which it was separate in Haswell and Broadwell, and they had to bring it back on because they have fewer rails. Right?
Yeah.
But could they be using these LVRs for the ring? And so it's one rail, but
not the ring. So, I mean, the one has, so if you have to go from separate voltages, you need to go through a circuit called a level shifter, unless they're really close voltages. And, those can add delays. Like, I don't know if you remember, like, with Barcelona.
Yes. Yes.
Right. They were like, yep, they had these, like, asynchronous FIFOs between domains, and it was just like a freaking mess.
Right. Because
it started adding variable latency, and it was a pain in the ass to debug. And, you don't do that unless you really need to and you have tight control over it. And, for the server guys, they're happy. There's the way they do the clock and power distribution is fine. I think on the client side, they just want to keep things real simple.
Yeah, they clearly do, and they have a lot fewer cores, so the stakes are different, and the workloads are different. So,
yep.
Okay, so let's talk a little bit about speed shift, and I want to introduce this because this is a thing, and you can tell me. Well, I think I got this down, but so we had speed step, and now we have speed shift, and yeehaw. They are different.
Well, we also had turbo boost.
Yeah, with turbo, which is speed shift, is kind of like... Anyway, all of it is some form of DVFS, right? Dynamic voltage and frequency scaling. And there are lots of different names and different marketing names for the same thing. The thing that we're doing is we're seeing the DVFS and Intel CPUs come under the control of the hardware itself rather than operating system software. And this has been an incremental thing. In Haswell, we got basically idle and active idle states being controlled by the CPU instead of by software. They did a lot of work around that for Haswell. So between keystrokes, if you're not doing much with your CPU, it's going to seek idle and do it very quickly because it's under the control of hardware and not wait for the OS to tell it. And then it'll wake back up when you press the next key and respond to that. Skylake takes it to the next step where the active working workloads, especially transitional ones, but everything is to some extent, the CPU is not 100% utilized all the time, very often at all. But the P states, the the active states of the processor.
Hold on. Let's be really clear about the definition of the P states into turbo and all this, right? So the P state is when the operating system says, "Give me 600 megahertz," or "Give me 800 megahertz," or 3 gigahertz, right? And that has always been under explicit software control up until recently, right? But then turbo mode meant that the embedded microcontroller controlled everything above the highest P state.
Right. So there was some autonomy with turbo.
Well, it's not just autonomy. It's also like, you can't, the software can't really tell things to run any faster than that because the software is too slow, and you could have a thermal event, or you could, run into all sorts of problems. And so basically, anywhere where you get close to the danger zone, right, the hardware takes control. And so, but the hardware is also way faster at responding, right? The OS is typically on a 30 millisecond polling loop to handle this stuff. Mm-hmm. And, they've got some embedded microcontroller in there. Who knows how fast it runs, but, clearly with the Fiverr, it was probably making changes, at a couple, at many megahertz. The Fiverr was 150 megahertz, so you could adjust the voltage, better than once a microsecond, I believe.
Yeah, and so speed shift is, well, ultimately you get rid of the software control entirely.
The software still controls, but it's more of guidance, and the hardware can fully control things if the software doesn't do anything.
Right. Well, the issue here is that you need Windows 10 with the latest patch in order to have the fully realized vision of speed shift, which is full hardware autonomy for clock speed and frequency. And the idea here is that if the hardware can set its own clock speed and voltage quickly in response to workloads, then it can be more efficient. And that turns right back into performance, because if you can get the work done and then go down into a lower state and save power, save heat, then when another request comes in where you need power, you can go up to a really high state, in turbo state, whatever, and get things done quickly. So you have more responsiveness because you were more efficient. And the OS, an OS doing it in 30 milliseconds is not going to get it done as well as a 1 millisecond response time in hardware, assuming that Intel has done a good job with its algorithms for understanding what's happening with workloads and responding to them well.
Yeah.
And that's complicated because they share power across the chip between the GPU and the caches and the Uncore and the CPUs, and they have to get all that stuff right. But I think they're pretty confident that they're already more efficient than whatever the software has done to now.
Definitely, right? So, I mean, the microcontroller can figure things out like, oh my God, this core is like, it's at the limit, it has 12 outstanding misses or 10 outstanding misses, whatever the max is. Like, he can't do anything. All right, let's just have him run at 100 megahertz until something comes back, right? Because you're waiting on the L3 cache or something, right? And that's like the kind of insight that the OS is never going to have. And, there's going to be changes in 100 cycles, right? Something is going to come back from memory. And so, 100 cycles is too fast for even the, this particular implementation to take advantage of. But, like, there have been academic papers, actually out of David Brooks' group at Harvard and some other places, saying, like, look, once you've got a core that's maxed out, you might as well clock it down, reduce the voltage, and then just wait for stuff to come out. And you can save power that way, but then you need super fast voltage and super fast frequency modulation. This isn't there yet, but it's a step in the right direction.
Yeah. And so basically, when you've got a legacy OS, even Windows 8 or Windows 10 not patched, you're still going to have, the CPU is still going to have to respond to the operating system hints and requests for certain parts of its power spectrum. And then when it can get into active idle or turbo, where it can kind of go beyond that, then it can go ahead and freelance. With Windows 10 and the latest patch, then it can pretty much be autonomous all the time. And so that's that's nifty. I think it gets us, something good. There's a couple other things that that they built in for power savings. One of them is duty cycle control.
Yep.
And they talked about this in relation to GPU and Broadwell, but this is hardware based for the CPU cores in Skylake, right?
Right. So a lot of this is driven by limitations of process technology, right? You can't drop your voltage below a certain point called Vmin. Mm-hmm. And generally speaking, you always want to run at the best frequency you can get at Vmin. And that's almost always the most power efficient point. And so the problem becomes, well, what if you're running like a really lightweight workload where you don't need a lot of performance? In fact, and let's say the minimum or the best frequency you can run at while at Vmin is like 1.5 gigahertz. But let's say you only need 600 megahertz of power. What they do is they will basically run it at 1.5 gigahertz and then shut it off like a third or two-thirds of the time. And so you sort of get an interpolated frequency of 600 megahertz. But you can't, obviously you can't shut it down for like a minute and then run it at 1.5 gigahertz for 2 minutes. You've got to be handling all your interrupts and everything. And so that is what the duty cycle control is all about. Is it's shutting things down and bringing them back up and delivering the right level of performance, but in the most power efficient way.
I think most people will remember duty cycle control from the Pentium 4 thermal throttling mechanism, right? That was DCC, right?
Man!
But it's the same thing. But in this case, it's a power optimization that's really smart. They can actually consume less power than this CPU would at its minimum efficient clock speed by doing this, and it still works. Like, it still all is transparent to applications and things. And there are a lot of cases where a CPU like this one is faster than necessary for just checking email or whatever. And this lets them shoehorn a big old core into a 4.5 watt power envelope. So it's a nice thing. Here's another one. They have a digital piece of hardware called a phase lock loop, which determines clocking in a CPU. And they have a digital PLL, or phase lock loop, in Skylake. This is the first time that Intel has done that?
Yeah, so most of Intel's clocking has traditionally been pretty conservative, so you're just using standard analog PLLs. And so, and let's be a little bit more specific here, right? You get some sort of clock signal in from the motherboard. You'll have like a crystal oscillator, or if you're really unlucky, you'll have a hamster in a wheel that's hopefully running at 100 megahertz. That's the
ASRock version.
Yeah. You said it, I didn't. I hope they aren't a sponsor of this show. And then you have to multiply that up, right? And so you got to take this 100 megahertz input, and now you want to get that up to like 5 gigahertz for the core clock. But then you have things like QPI, which are running at like 9.6 gigahertz, and you have like PCI Express, which is running at like 8-ish, and DDR runs at something else. So all these things take phase-locked loops or sometimes delay-locked loops. And let's not get into DLLs, but so that's what the PLL does, and it's a super tricky, very sensitive analog circuit. But what they did is it's now mostly digital. So there's one component, the VCO, voltage-controlled oscillator, that's still analog, but most of the rest you can do in digital logic now, and so that has a couple of advantages. It's lower power, which is great. In general, you tend to have a PLL per core on the server side. On the client side, you might have a PLL per core just to clean up the clock signal, but you don't necessarily have to. Like, certainly on some cheap, crappy mobile chips, they might have like a PLL for every core, and then they have to run at the same frequency for the most part. And it can make clock distribution harder. Mm-hmm. But so the other big advantage is because it's digital, shrinking it becomes really easy, right? Like, you can just take your standard tool chain from Cadence or Synopsys and be like, all right, I lied. I don't want 14 nanometer. I want 10 nanometer. Click. I mean, it's not that simple, but it's a hell of a lot more simple than trying to migrate analog circuits. And so,
right, which is one of the hardest things in designing, right?
Yeah, exactly. And this is like a very long-term trend, is that a lot of analog design is becoming increasingly digital. And, I think just part of that is analog is hard, and a lot of the advanced process technologies like FinFETs make analog harder. Right? And because with analog, it's all about precisely sizing the transistor so you get the right drive strength or the right balance between an NFET and a PFET, or this NFET and that NFET. And so it's very, very complicated. But with a FinFET process, well, what size transistor do you get? You get 1 fin, 2 fin, 3 fin, 4 fins, etc. So if you wanted really something where you had a ratio of like 1 NFET here and 1.5 NFETs over here, you're out of luck.
Right.
So, obviously, engineers can figure things out, but it might take more area or more power. And so by changing things to digital, that becomes a lot simpler. Intel's certainly not alone. I think there are other people who are going to be moving to digital PLLs as they get to 16 nanometer and beyond.
Yep. All right, let's talk about a sad bit of news that came out of our questioning that first day at IDF. Because we talked about this on the live stream last time. We talked about how the goodness of the Core i7-5775C, the Broadwell with the DRAM, and how it would be really nice to have a Skylake that had that EDRAM cache, because it turns out that the 128 meg EDRAM cache is really nice for gaming, and maybe the best gaming processor Intel makes is that 5775C, although they're still hard to get in the US. But presumably eventually Intel's telling us they're going to be out. I assume also alongside the Skylake stuff when they have a lot of 14 nanometer stuff, and that still could be another 6 weeks. They're selling a lot of them in Asia, but the North American market is not getting them as soon. But I asked the question, I told you guys I would, and I asked the question, will there be a socketed desktop version of Skylake with that EDRAM cache? Because they're doing more EDRAM caches for other versions of Skylake for the mobile stuff, for graphics, than ever before. They're doing 64 meg versions. They've propagated it down the lineup. But the answer is there are no plans for a desktop version of Skylake with an EDRAM cache. And so it's very unfortunate. I don't think that Intel has got a sense that like building a processor that's faster for games would be a good way to address gamers. Instead, they talked about B-clock overclocking. Because I know that a lot of those League of Legends players are really thinking about their B-clock.
Oh, yeah. No, I mean, that was... So there was a guy I talked to whose card I have somewhere. It's on my desk. Who's like the desktop marketing manager. And so I asked him about it. And he said that there were 2 issues. One of which is bullshit, and the other of which actually makes sense. And so the one that's bullshit, he's like, we're not really sure if what the performance actually works out to be. And I'm like,
you're Intel, you can model that. Pay the guy in that. I've been to that lab. Like this is not hard, right?
No, that's right. And it's like, even forget about that. Like, right, you guys have benchmarks, and Antec has benchmarks. Like, there's a few people that got the
5775C.
Whatever it is. That thing.
Yeah.
And, the performance is awesome. Like, it's totally... No, it's a no-brainer.
Right.
But when I talked to him later, what he said is, well, one of the issues, potential issues, is that if they can't reuse the desktop packaging, it's totally a no-go. And it basically doesn't matter how much you're going to sell them for, because there's I think it's like 37 millimeters by 37 millimeters. That's the size of package you get for the desktop.
Right.
You want something bigger, time to go talk to the Xeon guys.
Well, we talked about this in our story, because the mobile versions of Skylake that are out there have a wider package than 37.5 millimeters.
Well,
the ones with the DRAM.
7.5 millimeters is actually the right number. I mean,
I've got it right here. Let me pull this up. It's in front of my face here.
So the 6700K has a 37.5 by 37.5 package size.
Right. The U and H series processors with EDRAM are both 42 millimeters wide. So basically, the mobile ones with EDRAM are wider than the desktop chips. And the problem is you have to fit the Skylake CPU and the EDRAM chip on the same package together. And, they're both a certain shape, and they simply may not fit.
Yeah.
And so there are ways around that, but you have to change the shape of one of those chips probably. Or...
or you put it into the integrated GPU and just like cut it down pretty substantially. That might make some room.
Right, but then you're building another chip, and that's then a product that they're going to want to spend the effort on.
Yeah.
Right?
I mean, another mask is pretty expensive.
Yeah, and so that's a potential problem. The other thing, though, that I got out of some sources, David, was the possibility exists that this next generation, they're doing a third 14 nanometer. Refresh, because apparently 10 nanometer process has got some delays, so it's kind of tick-tock to do. and the to do is this Skylake or Skylake. Everybody pronounces it differently at Intel.
I think I've been told that it rhymes with maybe, so it's KB.
Skylake. It's possible that we could see a desktop chip with EDRAM in the Skylake time frame, and that one reason they didn't put it on the plan yet, or sooner, is in part because they were a little bit worried that if they tried to get one out for the Skylake generation, it would have the same fate as the Broadwell one, where the Skylake one was out right away after they finally got the Skylake one out. So it's possible that we'll see this configuration back somewhere around a year from now. And between now and then, the 5775C is still probably the best gaming CPU, better than the Skylake.
Yeah.
So buy that, I guess, is the answer. Or get a Skylake. They're all good for gaming. Gaming's not a particularly CPU-bound workload, which is one of the things we learned in our latest performance tests. So, we don't want to make too much of this, but it would be nice to see Intel pay attention to actual gaming performance and the features they build into their CPUs for the gaming market, which they give a lot of lip service to.
I mean, the thing is, I was joking about this in a talk, and I asked why they didn't have it, in one of the big sessions, and I didn't get a great answer, because there was an architect up there. But I think, I actually point blank asked someone, how much of a Kickstarter campaign would we need to get one? Because Intel is a company that responds to making money. And I think the point, the way I pitched it is, look, if I can get an equivalent of 500 megahertz more of speed out of, my gaming chip, that's worth at least $100 or $150, maybe $200.
Mm-hmm.
If you look at the price curve, on I've got the 6700K out here. What's the tray price? Tray price is $350, or box price is $350, right? So if I could get something that was the equivalent of a 4.5 gigahertz part, I don't think it's unreasonable to say charge $150 more for that, or $200.
Right.
And that embedded DRAM die is not super expensive, so you're not really adding a whole lot of cost. And, as long as the volumes are there, which for the best gaming chip out there, I think the volumes are probably okay.
Right. Well, that's the thing, is I think the answers we've gotten in the past when we've advocated for things like this have been around how many, of you and you and whose army is going to buy this? How many of your friends are you going to bring to this?
And I think Tech Report who reads an An Tech who reads Tom's Hardware Guide.
Well, I think right. PC enthusiasts will respond to this once they actually can purchase 5775Cs. And what Intel may find, if they put enough of these out there in the market, is that instead of upgrading to Skylake, people are buying these and either putting them into their Haswell systems or just building new systems around around them.
I mean, maybe. But, I mean, I think the key point is, like, did you buy a Titan? Okay, then go and buy this chip, right? It's a no-brainer.
Well, they do have the Haswell Lee stuff for the like super expensive folks. The problem is it's not actually faster for gaming.
Right.
Right?
Well,
I mean, this is one that you want because it is, right? It's actually faster for gaming.
yeah.
Okay, so we need to... We
Yeah,
are
next
over an hour in, and we have not gotten into GPUs. So
Yep.
I want to get into GPUs with a little introduction. And David, I think that we would say that this is the fourth or fifth revision of like a GPU architecture that Intel has shipped like in the past, like since GCN came out. Like,
Yeah, no,
like-
well, I mean, so Intel is on a, it's really a shame that Tom Piazza retired because he was, quite an interesting guy. But, he used to joke that, like, tick-tock is for sissies, and real men just go talk, 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 talk.
And he did it, right? The new,
Yeah.
the substantial new generations of GPUs have come out for quite a while, and we got Gen 9 now in Skylake, which there's a lot more EDRAM. If you look at the products, there's a config with 64 megs of EDRAM, which Tom told us 32 was really enough. So I don't know that.
Well, that was before 4K, right? So I mean, I think
right.
I could see 64 is now like kind of the minimum you want for 4K.
Yeah,
or maybe you need
how much
120.
4K are you going to drive with an IGP? I guess if you got to,
I would.
well, they're not using it for the frame buffer.
No, no. That's the whole point. It now can hold the frame buffer.
Are they putting it in there?
Yeah, so that was like the whole thing. So okay, we're just going to go straight to the architecture. Sorry.
But no, they changed the EDRAM. They changed the way it works. They changed what goes into it.
So the big thing is, like, before it was a victim cache, or explicitly controlled by the driver, and what that means is you evict something from the L3, and then that goes into the EDRAM, right? Or the driver sticks it in there. But the tricky thing is, it's still a cache, and you can't have I/O space sitting in there. So by changing it to a memory side cache, what that means is it contains the same stuff as memory. So anything that can be in memory, like frame buffer,
right,
like your display output, can be in that EDRAM. So what's really cool is, now you look at a notebook and you're like, okay, screen's not changing that much. Shut off the DRAM. We'll just use the embedded DRAM. I mean, maybe if you're super lucky, you can get away with just using SRAM, but that seems a little unlikely. The L3 cache ain't that big. But, certainly there's, that's pretty awesome, right? Or you could see, even playing a DVD, right? You stream in like 128 megabytes, which I don't know how many seconds or minutes that is. Like a Blu-ray is like 50 megabits per second. Is that right?
Sounds right, but I don't know off the top of my head.
Okay, so that could hold on the order of, like, say, 15 seconds of a DVD, of a Blu-ray, right? You shoot it, well, okay, so let's just say 10 seconds. You shoot it into the EDRAM from your memory, you shut down the memory for 10 seconds, and then, you proceed through and chunk it, read it into the L3 cache. You do your magic decode, and then you shoot it right out through the embedded DRAM, and boom, you've saved yourself a ton of power.
Yeah.
That's cool.
Yeah, there are a lot of nice things that you can do with that once it's there. And yeah. And so we have now also changes to the GPU microarchitecture itself. Well, okay, first of all, EDRAM bandwidth. I thought this was an interesting answer. I asked, is it higher bandwidth? And they said it is at least no slower. Like, they weren't going to tell me exactly what it was, but at least no slower.
Yeah.
I heard someone else say it's the same, but the person who said at least no slower was an architect, and they were more careful. And so I'm curious to see what is behind that, and whether maybe we can measure that once we get our hands on one of those things. Because you can just measure it with the cache tool. So
right.
Anyway, So the EDRAM is tied to the or used by the GPU, and then the GPU itself is DirectX 12 capable in all. And I guess we should put a marker down and say DirectX feature sets are less important over time, as we've already worked out like the data type stuff and most of the fixed function hardware stuff, and additional hardware features are nice, but they're not always the end all be all. You're going to run DirectX 12 on a Gen 8 Haswell IGP. It's just not going to be as full featured. You're not going to get all.
Well, no, I mean Haswell doesn't. I don't think it has DX12.
Does it not? I thought it did.
I mean, I could be wrong, but I think the interesting point here is that Intel is the first out the door with like full feature level, full everything on Skylake.
Yeah.
Yeah.
More so than Maxwell.
Yep.
More so than GCN.
Yeah, and that's pretty amazing. And so there's a great slide in their presentation on graphics where they're like 6 years of processor graphics, starting with Iron Lake, which was DX10, 32 nanometer in the chipset, and 10 EUs and 43 gigaflops at 1 gigahertz. And now it's like a teraflop DX12, plus you've got the better EDRAM and you've got 72 EUs. And, there's just, I mean, it's really remarkable how graphics has gone from being like this redheaded stepchild where they're like, well, we need this many pins on our South Bridge, so you can have a bunch of blank space and sure, play with it. To now it's like, yeah, these high-end GPUs are way bigger than CPU cores. And so there's been this dramatic shift. And then also, I mean, I think the big challenge for Intel is monetizing it, right? And getting people to pay more for that incremental silicon area. And clearly they have figured out how to do this to a certain extent. Otherwise, they would not be plowing quite as much area into the GPU.
Yeah. Well, and more than the CPU cores by a substantial amount, plus the EDRAM externally, which adds cost. There's a lot there. And the technology that they put into this Gen 9 core is substantial to develop, right?
Yep.
So JTS888 has a question. Since he says, looks like Skylake is the only GPU APU to fully support every tier of the DX12 features, including the optional extensions. Could you guys discuss the performance and quality implications of some of the features? Raster ordered views, conservative rasterization, stencil ref values from shaders, resource binding tier 1. Anyway, he goes on. I want to pick out a few of them, and we'll talk about them real quick based on what I understand them to be. The thing is that it's hard to know the performance implications, but there are some things that they do that are useful, right? Raster ordered views, as I understand it, is what Intel called pixel sync several generations ago, that they introduced, and basically has now been moved into DX12. And that feature, one of the things that can allow is fast real-time handling of order-independent transparency, which is a difficult problem in graphics. So ROVs are good to have for that reason. Another one is conservative rasterization, which is about being able to look at a grid of pixels and basically say yes or no, this pixel falls within the boundaries of this geometry. And
well, it's not just that. It's like the difference between regular rasterization and conservative is, in some cases, you would have different tests. So you'd say, you might have one test that says, is this pixel fully within the triangle?
Right.
And then you might have, does this pixel get touched by the triangle? And so I think the difference with conservative rasterization is that it allows you to have a much more flexible first-order primitive to say, like, give me a test, give me the set of pixels that are touched by this triangle.
Right, and that's useful for things like evaluating voxel structures. NVIDIA talked about doing a global illumination algorithm using that. And global illumination is one of these like graphics holy grails where you have like unified lighting in your software engine where basically all the light bounces around and reacts and interacts in shadows. And
they should just ray trace it.
Well, they're not far from it with global illumination, right? It's just that you have to be fast enough to do things in real time. And this is a thing that people are starting to do now, but having hardware to make it easier is kind of a big deal, and it's something that they should do. Some of the other things that they have, like tiled 3D textures and some of the resource binding stuff, can allow potentially for games to stream in tons of data as you go through the game world. Have the GPU kind of control accessing these resources and just use a whole lot more, like some of the mega texture stuff that they've done, but have the GPUs use a whole lot more unique texture data to populate the world. And then the low precision 16-bit floating point is just another data format. Weirdly, DirectX 11, it cleaned up everything to make sure that the data formats were really good and deep and precise, but that burns more power when you have
I mean, you don't always need it, right? So there's a lot of things where it's nice to have it in floating point format, but you sure don't need 32 bits. I mean, and so handling, it'll be interesting. I haven't talked to David Blythe or any of the other folks about this, but if they can actually do native 16-bit floating point, right? So you take a whole, I think, 256-bit vector, break it up into 16-bit floats, that could potentially double their performance and drop power consumption and use less memory bandwidth as well. Actually, they probably could do that anyways. But it just makes everything go a lot more efficient, right? Yeah. And that's huge.
Yeah. So these things are nice things to have, and especially, I guess I would say, in the scale of Intel's graphics, which is relatively small in the PC world compared to the big discrete GPUs, having the performance is of having the full performance of all these features instead of having to find alternative algorithms to do these things is good, right? And there's some future proofing involved in here too. So, okay, so we need to wrap soon. We've been at this for a while. David, are there particular questions that you think we should definitely? We've got more questions than we can answer.
We'll have to go another week. So I think there was a bunch of questions about.
Ashes of the Singularity, DirectX 12.
We got to some of that. The async compute shaders, right? That's a really interesting thing. So
should we set that? Should we set that up? Because there was a benchmark that came out while we were at IDF.
Yeah,
right? I didn't touch it, but it was basically the guys building a new game at Oxide Games, Dan Baker. They have a benchmark. It's one of the first DirectX 12 benchmarks, and what it showed was basically there was a more gain for a Radeon going from DX11 to DX12 than for a Maxwell-based GeForce, generally speaking.
Which is exactly what anyone should have expected if they knew the architectures, right?
And one of the keys to that was that the Radeon has these structures called asynchronous compute engines that have been there since the first GCN 7970s.
Right. But the thing is, it's interesting to know why it was put in there, which is because this is not in any DX. GCN was explicitly designed for the consoles. Mm-hmm. And so the consoles do have this because they've always had this very low level, DX12 mantle, metal, Vulkan-like API. And so, AMD put it in there, and it really didn't help them for a long time. But then, NVIDIA, not having any console business, didn't really care. Right? There was just no motivation to put it in because it was a feature that no one could use. Right. And so, what this lets you do is you can have compute shaders. It's kind of like simultaneous multi-threading for a CPU, where you have essentially, you can have your graphics or your synchronous compute shaders running at the same time as an async compute shader. And so because you can get multiple shaders in the GPU at the same time, you can more fully take advantage of all of the cores, and you can make more use out of the hardware. And so this is actually really useful for things like VR, where you can use your async compute shader for things like a perspective warp. I would assume that NVIDIA and AMD will figure out how to get this done in the future. So for Pascal, I think, I'm just looking at this question right now, and I see he's also asking about Pascal's arrival date is a really interesting question. So,
and that's the generation beyond Maxwell,
right?
Of NVIDIA GPUs. Yeah.
So here's the thing. NVIDIA needs to get this out as soon as possible, not because, they're doing fine on the graphics side, but Knight's Landing is coming out this year, and that's Intel's high-end HPC-oriented part. And the thing is, comparing raw specifications, it's better than any of NVIDIA's compute products. Just in terms of peak flops and memory bandwidth and all these other things. On top of that, it's fully x86 compatible. It doesn't need a host processor. Flavors of it will come integrated with OmniPath, which is Intel's version of InfiniBand. And so it's going to be a real monster and be very attractive for HPC users who haven't looked at CUDA. Right, so if you've already bought into CUDA, you're going to be happy with NVIDIA. You're going to probably stick with them. Mm-hmm. But if you're on the fence, you were a little slow, your app wasn't supported, Knight's Landing looks really great. And so NVIDIA is going to be under huge competitive pressure to release a high-end Pascal as soon as possible. The wrinkle is, as JTS 8888 pointed out, well, if they're using HBM2, the availability on that's not clear. That's expensive stuff. Right, this 2.5D packaging is not cheap. Joe Macri aside, I was at lunch with the guys who did Hybrid Memory Cube, and they flat out said Hybrid Memory Cube is less expensive than HBM. Period. And not only that, but HBM is not really, a super mature high volume technology yet. It's getting there. And then they're also working with TSMC's 16 nanometer process. And so the real interesting question is, when can NVIDIA actually and TSMC yield out, a giant die? Because, right, the first Maxwell chip, if it's targeting HPC, it's probably going to be 400 millimeters squared. Right? And I cannot name a single product, except for an FPGA, and those don't quite count because they're different, that is yielding on TSMC's 20 nanometer process in like really good volumes. Like Oracle has some server chips, haven't seen them go into production yet, really. So there might be problems there. On the other hand, like if I was NVIDIA and I had the ability to do it, I would launch that guy at supercomputing this year in November to take the wind out of Intel sales. So, you know, what's going to happen there? That's a really interesting question. It depends on how aggressive NVIDIA is moving to new process technologies. I mean, clearly they have a need to do so, but, you know, my observation is that historically, NVIDIA was much less aggressive about process technology. When they got aggressive, they got burned. Mm-hmm. But NVIDIA is also they have much better physical design than they used to, and maybe it's something they can pull off now.
Yeah. So yeah, Ashes is a singularity.
Yeah. Well, I mean, I would expect that Pascal has the ability to do asynchronous compute shaders, right?
Well, and this is. Yeah, there's a lot involved in the question here because, Dave, there are people who are like at least posing online as GeForce owners. I doubt they're real people, but I don't know, who are saying they're going to send their GeForce cards back because they don't support asynchronous compute engines the same way as GCN. Because they're afraid that
guys
they're afraid DirectX 12 won't run well on GeForces.
Okay, so obviously AMD is going to get a much bigger benefit from a DX12, right? In part because their drivers are just not as good as NVIDIA's. But look, so for every person out there on the internet who is really unhappy with the performance of your Titan card or your 980, like, shoot me a line, I'll take it off your hand. Right, like, you can go out and buy a Radeon. Like, if you want to go get yourself a new graphics card, whether it's NVIDIA or AMD, but if you think that 980 just isn't going to cut it because it doesn't have asynchronous compute, send it to me. I'll take care of it and put it in a good home.
Yeah. So there are three things with asynchronous compute that I want to understand the difference between, like say Fiji or Hawaii, the big GCNs, and Maxwell, right? And because there are three separate things I think that I would put into important categories here. One of them is the ability to queue multiple different types of work.
Yep.
And NVIDIA has had
not just queue, but also you can queue it, but you want to get it into the shader array. You need to dispatch it, right?
Okay. So let's yeah. So you want to have that. NVIDIA's had the ability to do that since Fermi, I believe. They've had this hyperqueue feature in the big chip. No, it was in GK110. GK110 is where they 32 different queued items in hardware.
Right, but I think they have to be of the same type. I don't think
that's the other one. Is can you run kernels of different types on the GPU concurrently? Right. And then the last one is preemption. Right.
Yeah.
You got to be able to, like, especially if you can't run different things concurrently. Like, you need to stop and start something else. And what does that look like? Right.
So I've been told by folks at Oculus that the preemption is, and this was prior to the Skylake Gen 9 architecture, which has some better preemption, but that the best preemption support for context switches was with AMD by far.
Right.
Intel was pretty good, and NVIDIA was possibly catastrophic. The real issue is if you have a shader running, a graphics shader, you need to let it finish. And, it could take you a long time. It could take you over 16 milliseconds to finish. I mean, I have heard from and this is from engineers who are working on really crazy stuff in the driver of graphics shaders that took a couple seconds to run. And obviously something is totally busted.
Right.
But
it's completely unworkable for real time anything. Right.
Yeah. I mean, this is really great for your PowerPoint slideshow, maybe. But the point is, and NVIDIA is very, to their credit, they're open and honest about this in how you tune for Oculus Rift, is that you have to be super careful because you can miss a frame boundary because the preemption is not particularly low latency. And again, it's not like this is a bad decision on the part of NVIDIA. It's, that's what made sense. And preemption wasn't something that was super important when the chip was designed, and the API support there wasn't as much bang for your buck. And so now, I'm sure they're going to improve that in Pascal, right? Yeah. NVIDIA is full of good, sharp architects, and they'll probably fix it in Pascal.
Yeah, well, and that is one of those things that they kind of projected better preemption for Maxwell, but then they didn't build a Maxwell for GPU compute like HPC type scenarios, right? They don't have a big one for that.
I mean, Maxwell's not really a great fit for compute because I think the way it got more power efficient is they threw out a lot of the scheduling hardware, almost all of it. And again, NVIDIA hasn't talked about this, but and that's a fine thing to do. It increases your power efficiency, especially for graphics where you can compile it ahead of time, and you generally know that they're going to be doing same stuff. The problem is, in compute land, you can never be sure what your crazy users are going to do. So the value. I mean, look, Intel has a full-blown out-of-order core in Knight's Landing. They didn't do it because they're dumb. Right. They did it because it's a good idea. And the point, well, I mean, they also want to be able to run sequential code, which a GPU just can't really do, period.
Right.
But, I mean, the point is compute workloads are sort of inherently unpredictable. And so some of the tricks that work great in graphics are just not amenable to compute. And we've seen this historically, right, where there's a different core with more shared memory and different double precision and single precision balance,
right,
for NVIDIA's HPC parts. And so I think they just looked at Maxwell and they said, look, these are the resources we have. Here are our competitive pressures. Just do Pascal.
Yeah. And it makes sense probably. I mean, I can see that because the GPUs that we have, Fiji and Maxwell GM200, are really kind of retargeted because 20 nanometers didn't work out. And so, yeah, I mean, they're what they had to do at the time.
Yeah, that's right.
Okay, so I think David, we should probably wrap it. I know that you need to probably eat some dinner and relax, and I understand you had a busy day.
The eat is a pressing concern.
Yeah.
So for everyone on the podcast, I actually rode my bike 40 miles up to John Petty's office today and had lunch with him and then came right back, hopped in the shower, and then got on Skype.
So there you go. So yeah, so did he share any market share data with you about GPUs or?
No, I mean, we were mostly talking about, just interesting things we'd seen. He was headed on his way to China in a couple of days. But, it's, there's not a really big community of it's like we always go to, when I get to go to NVIDIA events, it's John will be there, you'll be there, someone from an Antec, and there's, sort of a small brotherhood. Now that Anna Filatova's gone, it's pretty much exclusively a brotherhood.
Yeah.
Folks who are in the sort of PC server graphics space, and it's always fun to catch up.
Yeah. Good. Well, it's fun to catch up with you around all this stuff going on with Skylake, David, and it feels like we didn't have enough time to really even touch on some stuff, but hopefully folks have enjoyed it. Thanks to everybody who was in the live stream with us and who asked questions and who tuned in and listened. And we will have to do this again sometime soon. Maybe around something interesting, and maybe I don't know. We'll have to figure out what the next thing is that would trigger this, David.
So, I mean, at some point I'm gonna be writing an article on Skylake graphics. So maybe that'd be a good thing to do. Also, by the way, that was 40 miles round trip, not 80 miles round trip. I'm okay on a bike. I'm not that awesome.
Yeah, I saw that math in the chat, and I was like, who thought that was what happened? So I guess they thought you look really tired. I don't know.
Yeah, maybe I needed to get some coffee beforehand. I don't know. But yeah, Skylake graphics would be interesting to talk about. Broadwell EP will be later this year.
Yep.
And maybe fingers crossed, we'll see Pascal this year. I mean, I actually really want to get. I would really love to be at the launch for that. I think last time I was not at the launch for the Titan, and I think that was a totally missed opportunity.
Yeah. Okay. Well, thanks again. Thanks everybody. We'll do this again soon. Everybody, take care.
All right. Good night.